This is the last session of the whole course, in the theory part at least. I still have a backlog of problem-solving sessions to film, but this is the last session in the theory part for the whole course. Okay. Right. So from the previous session, we had the equation plus circle, and that was the ratio of these exponential terms, so e to the minus energy divided by kt. So your n of k divided by n of m formula from the previous session. Have a look if you've forgotten. Okay. So the downward transition rate, the spontaneous emission, so particles get, photons get emitted, and the particle, therefore, majority of the particles will therefore have lower energy, right? Conservation of energy, approximated. Okay, now you can write down a formula now that relates these rates of well, I'll just state it, so it's probably clearer just to state it. Now, can you see it? Let's take the case where now k is our starting state and m is our final state after the transition. Let's say, okay. So you have a higher energy starting state and a lower energy final state. So ek is greater than en. Let's say. Now. So let's say you have a proportion of your system, quantum systems, whatever they are, in state k, right? And they emit spontaneously photons and take a lower energy state m, okay? Now can you see, does it seem reasonable to you that these are the proportions, so the proportion of systems with energy Ek is the proportion of systems of energy En, right? So initial energy Ek and final energy En here. Now, does it seem reasonable to you? You've got a kind of balancing equation here. So the rate of stimulated emission plus the rate of spontaneous emission, in other words, the total rate of emission, right? So particles being shot out, photons being shot out, so the energy level will go down, and the energy is taken up, it's stimulated. So in a sense, the energy coming from the higher energy, the initial energy, the initial state, is then being absorbed by other systems to take them to. Does that make sense? Hold on. N is less. These paradoxes. When the text is not clear enough that a professor starts having trouble with it, then if you're in the same boat, then you can understand. Anyway, this is from the text. I've put it in bars, double bars here. I thought I understood it, but now I'm having doubts. Anyway, you have this equation is the equation of balance, that the rate at which particles are emitted must balance the rate at which those particles then get absorbed, because nothing's destroyed. So it's a kind of conservation type equation, okay? And it would help. Now, this is just thrown at you in the text. It would help to have more explanation but there's only, only about half a page in the textbook left, so it's a bit thrown at you, and somewhat confusing. Well, I found it somewhat confusing. Okay, but anyway, so assuming this balancing equation is valid, okay, so we can use the plus circle equation, the ratio of the exponential terms, e to the minus energy over kT terms. So we can use that equation. So nk divided by nm. So we can use that. We can use the rate equations that we've found. This was the rate of absorption. Sorry. The rate of stimulated. No, I can't remember which one it was, but this was a stimulated rate. Okay, so we've done that equation earlier, right? And previous session we derived this equation for the spontaneous rate of transition, this one. So we can plug these into this balance equation, and that will allow us, and I've got an I here, so we can actually solve for this I, the so-called intensity. Right? You could try that for homework if you can follow it sufficiently. I have a question mark about what this is, so give that some thought. See if you can make sense of it. Right. So you plug these rate terms, rate equations here and here into this balance equation, and then you can solve for this I, and here it is. Now, this formula here is veritably famous. It's like it's the famous, ultra famous Planck black body distribution formula. Like if you heat up metal, it'll glow orangey red, and you heat it up more, then it'll be sort of yellow hot. And you really heat it up and go white hot. So depending on the temperature, a body will radiate energy at different frequencies, and the proportion of the energy at each frequency the curve will look somewhat like that. Now this Planck, who was investigating that formula, that looks like this. So here is the frequency of the emitted light, and this axis is the proportion of the particles having a given energy, photons. I didn't know. You didn't know about photons when you did it. So I'm not quite sure. So the vertical axis would be what? The proportion of the energy distribution. I'm rusty on Planck's formula. Anyway, this we've now derived from this balance equation Planck's famous it's called black body radiation formula. Why black body? Well, imagine a great block of metal, and it's hollow. There's a hole inside it, and with a tiny tunnel, very, very thin tunnel, like an entrance into that internal hollow space. And so you heat up the metal, and the radiation that is emitted from the internal surface. Imagine inside the metal there's a hollow sphere. Imagine, and so on the surface of that sphere, your light will be emitted, and then later will be absorbed, because there's nowhere for it to go. Right? Anything that gets emitted has to be absorbed. So no light gets out. So in that sense, it's black. Okay, so that's why it's called a black body. Now, to investigate it as physicists, experimental physicists, you have to look at something coming out. So that's why you have this tiny little tunnel. So light does come out, and you observe the distribution of the energy at various frequencies, and you'll get the Planck the curve that looks like this. And the proportion of the energy, I guess, and the frequency of the light coming out along this axis. And this formula here gives correctly that the experimentally observed distribution. Now the reason why it's so famous is it's the beginning of